Hi everybody! So in today's video, we're going to be learning about Unit 1, Lesson 5, which is how to estimate limit values from a table. So there are two learning targets today. I can estimate the limit of a function, either one-sided or two-sided, using a table of values, and I can justify why a limit does not exist using limit statements when necessary. So just like in our previous examples, we're going to be finding one-sided and two-sided limits. What makes today different is that we're going to be given a table of values for the function instead of using the graph of a function. The other thing we're going to be doing is justifying our answer, so explaining our thinking using limit statements, which means our notation that we use is going to be really important. We want to make sure that we're using the correct notation so we communicate our mathematical thinking correctly. Just like when we estimate the value of a limit using a graph, we can look at one-sided and two-sided limits using a table of values. Remember, when we ask you to find a limit, we're just saying, what are the y values as x gets close to a certain number? So if we look at this table, the first thing to notice is that the x is the first row and the y is the second row. The second thing to notice is that the number 7 is in the middle of the table, and the x values are progressively closer to 7 on both sides. So 6.99999 is almost 7, and 7.0001 is almost 7, and that as you get farther away, the numbers get farther away from 7, all the way to 6 and to 8. The y values are what we're going to look at to evaluate these limits. So the first limit says the limit as x approaches 7 from the left. So if 7 is in the middle, the left side of the table would be this side of the table over here. So as we approach the 7 from the left, we need to look at what the y values are doing. It looks like the y values are approaching negative 1.925. Now you might notice that it says undefined here. Remember, we're not paying attention to what the actual function value is. It's possible that on the graph there's an open circle when we get to the actual point. All we really care about is that this number is negative 1.925. So here we would write negative 1.925. Now I should note here that we're always going to use 3 decimal places. In calculus in general, you are required to always use 3 decimal places when rounding. And you don't actually have to round, you just have to truncate, so stop after 3 numbers. The next problem says to find the limit as x approaches 7 from the right. So the right side of the table would be this side over here. If we approach the 7 from the right, the y values are approaching negative 1.92. And again, 8 rounds to 5. So we would say negative 1.925. Now what that means is that the left side limit and the right side limit agree. So if I were to ask you about the two-sided limit, you would say, since these numbers agree and both sides are the same, the answer would be negative 1.925. Again, the common mistake here is that students think the function value, which in this case says undefined, might affect their answer. The value of the limits. It doesn't. So don't let that undefined that's there in the middle of the table confuse you. It does not matter what happens at 7. You can almost pretend like this isn't even here in the first place and just pay attention to the numbers around it. Let's go ahead and try a few examples where we can see this in action. So in this table, you're going to notice that in the x row, we have 0.99, 0.999, 0.9999, and 99999. And on the right side, we have 1.00001, 1.0001, 1.0001. All of these numbers are close to the number 1. Now, in this table, there is no column for what happens at the number 1. We can kind of imagine that the number 1 would fall in between these two boxes on the table. Now, you might think, well, how am I supposed to find the limit as x is approaching 1 from the left, 1 from the right, and 1 if we don't even have a box for the number 1? And what I will remind you is that what happens at your function value, what happens at 7, for example, doesn't matter. So we don't even need it included in our table to still successfully find the limit. If we want to find the value of the limit as x approaches 1 from the left, we would just start from the left side of the table and slide towards 1. Now, if we look at the pattern here, it's 1.9949, 1.9995, 1.9999, 1.99999. Those numbers are getting bigger and bigger and closer to the number 2. So we would say that the limit from the left is 2. Now on the right side, if we slide closer to the middle of the table, we've got 2.0049, 2.0005, 2.0000, 2.0000. Again, the numbers as we slide towards the middle are getting closer to the number 2. And last but not least, if we wanted to find the two-sided limit, we would compare these two answers, which agree, which means the two-sided limit is also 2. In the next example, if we take a look at our table before we even start finding our limits are always asking us what's happening as x approaches 0. There is no box for what's happening at 0, but if we use our imagination, we can imagine that 0 would be in between these two boxes, because 0 is where you cross from a negative to a positive number. Now, if we want to find the limit as x approaches 0 from the left, we would just slide closer to 0. If we look at these y values, we've got 0.9996, 9997, 9998, 9999. We're progressively getting closer to 1, so my limit value would be 1. On the right side of the table, if we slide closer to 0, we've got negative 0.9996, 9997, 9998, 9999, so we're getting closer to negative 1. Now, if we want the two-sided limit, you're going to notice that this time these two limits do not agree, which means we would say that the two-sided limit does not exist because the limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right of f of x. For our next table here, we're asked to find the limit as x approaches 2. Now you'll notice that in this table, the 2 would lie right in between kind of these two boxes, the 1.999 and the 2.0001. If we approach that box from the left, we've got 1.336, 335, 334, 333. So 1.333 repeating is like 1 1/3. You should know that 1/3 is 0.3 repeating, which means my answer here would be 1 1/3 or 1.3 repeating. Now on the right side, if we approach the middle of the table, we've got the same kind of pattern going on. So I would say 1 1/3 or 1.3 repeating, which means that the two sides do agree. So my two-sided limit would be 1.3 repeating or 1 1/3. Last but not least, for problem number 4, we're trying to find the limit as x approaches 8, which would fall in between the 7.999 and the 8.00001. If we approach that box from the left, we've got 1.5292, 5293, 5294, 5295. So it seems like my limit would be 1.529. because that's kind of the part that's staying the same this whole time. If I approach from the right, I've got the same kind of pattern going on, 5298, 97, 96, 95. So I would say 1.529, which means that since these two limits agree, we would have 1.529 1.529 as my answer. One common mistake that I often see for evaluating limits from tables is that students don't think that 1.529 is an acceptable answer. They want to round that to like 1.5 or 1.5297 or something crazy. You have to go with the numbers you have. The numbers you have, the 1.529 stays constant for the entire table. So clearly that's an important number that we're getting closer to. So I would go with 1.529 as my limit answer. Remember, a limit is asking what you're approaching, not what is the actual number that you have in front of you. So 0.9999 isn't 1, but it's certainly getting closer and closer to 1 if we look at the pattern of behavior in these numbers. 96, 97, 98, 99, it makes sense that the next number in the pattern would be 1. And that's kind of how you want to think about this. What is the trend or what is the pattern in the table? Thank you guys so much for watching. I hope you have a wonderful day and I hope to see you soon.